In passive systems, also known as thermosiphon systems, the tank sits above the collectors. Colder water sinks into the collectors, whilst warmer water rises unassisted from the collectors into the tank. The tank may sit on the roof with the collector, a close-coupled system, or within the roof cavity above the collector, a gravity feed system. With these systems, the roof support structures must be strong enough to handle weights of up to 800 kilograms. Active systems use a small pump to move water between the collectors and the tank. The location of the tank can be within the roof or on the ground. Each type of system has advantages. A passive system is space-saving and is easy to maintain with no moving parts. An active system is unobtrusive, lightweight, can use an existing tank, and the tank can be located closer to where hot water is used, reducing heating loss in pipes, but the pump uses some energy. There are two collector types to choose from: flat plate and evacuated tubes. Evacuated tubes have the advantage of receiving perpendicular radiation for a greater part of the day. This, combined with their vacuum insulation, means good winter performance. Flat plate collectors, particularly if purchased as part of a closed couple system, can be more affordable than evacuated tube collectors. However, the prices of evacuated tubes has fallen in recent years. Collectors should ideally face true north in a shade-free position. Facing the collectors 45 degrees from the north will result in only minor reductions in performance. The ideal inclination is the angle of latitude plus 5 to 10 degrees. Sydney's latitude is 33.5 degrees, so an ideal angle of inclination would be around 40. However, plus or minus 15 degrees would still provide adequate performance. If your collectors face due east or west, the lower the angle of inclination, the better. However, to allow thermosiphon flow, you must always keep the angle above 10 degrees. For the correct sizing of your collectors and tank, consult manufacturer's guidelines to see what is best for the climate and household. In places with minor frosts, evacuated tubes may offer enough inbuilt protection. In climates with regular frosts, indirect or closed-loop systems are the most popular and reliable form of frost protection. Instead of water, an antifreeze fluid is heated in the collectors. The antifreeze passes heat onto the water via a heat exchanger. The antifreeze does not come into contact with the household water supply. Other frost protection methods are available, such as frost protection valves, temperature programmable pumps, and drainback systems. In an Australian summer, water in collectors can easily approach boiling point. This can cause excessive pressure buildup and can damage the lining of vitreous enamel tanks. The Australian standards state that solar hot water systems must provide over-temperature protection without draining water, so a temperature pressure relief valve is not enough. The most common way to prevent overheating in the tank is by automatically stopping the circulation between collector and tank when the tank water gets too hot. This can be done using a solar control valve or a temperature
turbulence and increase heat stratification. Open-loop drums with minimal turbulence can also be designed to encourage the heat stratification process. We know this may be accomplished by simply allowing hot water from the collector to enter the top of the drum, and by returning cold water from the bottom of the drum. As long as the turbulence created by the incoming water is not excessive, we can expect layers of water to stratify according to their temperature differences. The process of heat stratification may also be favored by using multiple drums. Multiple drums are used to effectively process the incoming and outgoing water. As previously mentioned, heat storage systems can be modular, and individual drums may be daisy-chained together to increase the heat storage capacity. Once individual storage drums are daisy-chained together, they may be enclosed inside an insulated chamber, and household air may be blown across them to extract heat. This simplifies the construction and assembly of heat storage systems and facilitates the combination of a domestic hot water system with a home heating system. I've developed 4 types of multi-drum modular heat storage systems. This one is used with a closed-loop collector. It uses an input heat exchange loop and an output heat exchange loop inside each drum. This closed-loop multi-drum domestic hot water system was built by Scott from Plattsburgh, New York. Open-loop drain-back and trickle-down systems can also take advantage of the multi-drum heat storage concept, as long as they are assembled to minimize turbulence. This is accomplished by minimizing the velocity of water passing through the storage drums while maintaining a healthy flow rate. Large diameter pipes may be used to do this. I've used 2-inch PVC pipes pressed through the top lids of plastic drums. The input pipes are only a few inches long, but return dip pipes are 4 feet long to siphon cold water from the bottoms of the tanks. This method works fine, as long as the connecting pipes are filled with water. Heat stratification pipes provide another method of connecting drums of water. To simplify the connection process, I modified a PVC pipe that would pass right through the rubber boots installed in the drums. The large holes drilled on the tops and bottoms of the PVC pipe were designed to minimize turbulence by minimizing the flow speed of the hot water entering the drums. It was my hope that the slow-moving water would maximize heat stratification by allowing natural convection currents to carry hot water to the tops of the drums.